Hey everybody, how you doing? Mr. Elliott here. I'm so sorry that you're not getting the snow that you so desperately wanted, and you're going to have to deal with school and Elliott and all that good stuff. But I want to point out really quick, on a snow day, wouldn't it be awesome you could still do your math homework on Sunday because of these video lessons? Awesome. Or I guess on Monday. But that's one thing I've thought about. Like if we have school like this, snow days would become obsolete. Okay, so last lesson was absolute value inequalities. Today we're going to be dealing with absolute value inequalities that are greater than. If you've not yet watched the less than video, you might want to go back and watch that one. I have 4 or 5 examples for you. I actually have the exact same number of examples for you as we did on the previous lesson. I'm just flipping the less than to a greater than and seeing, well, what would happen with this inequality if I flipped it around. Now, when I look at these problems, I always forget like what I'm supposed to do with it in terms of like, is it the and problem? Is it the or problem? So I like to think of a simpler one. So instead of thinking about absolute value x minus 3, think, well, what if it was just absolute value of x? Absolute value of x greater than or equal to 6. Well, what would that scenario be? If we think about it graphically, you've got 0, let's see, 0, 1, 2, 3, 4, 5. Those numbers are all less than 6, so that wouldn't fit. But once I get to 6, 6 is equal to x, and then a 7, 8, 9, 10, 11, 12, 100, a billion. All of those numbers are all greater than 6, so it would be like that. -1, -2, -3, the absolute value of -3, -4, all those numbers are less than 6, so it's really empty from -6 to 6, but the absolute value of -6 is equal to 6, and if I think about absolute value of -7, that's greater than 6, and so on. So this is what a typical or a typical greater than graph looks like, which this is a typical or statement. So x is greater than or equal to -6, or x is less than or equal. I made a mistake. Either x is greater than or equal to +6, or x is, flip the inequality, less than or equal to, change the value from +6 to -6. Or if you go with interval notation, -infinity to -6, soft on -infinity, hard on 6, union 6 to +infinity, hard, soft. So kind of the 3 different ways that you would be responsible for. Now, if you can make sense of this situation, you can make sense of this one. The setup is exactly the same as it is down here. Either this x minus 3 is going to be greater than or equal to 6, or, do I have to write the word or? Yes, you have to write the word or x minus 3 is, flip the inequality, so less than or equal, and change the value from positive to negative. The reason you have to write an or is because, remember as we said in our conceptual lesson, it's either an and problem or an or problem. If you don't include the or, the reader wouldn't know if you're trying to do an and problem or an or problem. And once you get to those special cases of the ands and the ors, it gets really weird really quickly. So anyway, we have this or statement. And then add 3 to both sides of this inequality, and I get x is greater than or equal to 9. Add 3 to both sides of this inequality, and I get x is less than or equal to -3. And I still have this or statement. Graphically, either x is greater than 9, greater than or equal to 9, or x is less than or equal to -3. That's exactly what we expect out of an or statement, so there's no weird answers here. -infinity all the way up to -3, soft, hard, union 9 to infinity, soft. So if you understand this example essentially works the same way. Okay, let's see this next one. Example 3. So let's say I had absolute value 5 minus 2x, close absolute value greater than 10. Well, if you struggle with what you're supposed to do with this, think, well, what if it was a lot simpler? What if it was absolute value of x greater than 10? Well, if it was this scenario, that's the one where you have a number greater than 10 or a number less than negative 10. Yeah? So either x is greater than 10 or x is less than negative 10. So I flipped the inequality, changed it from positive to negative, and I slapped an or in between them. Same scenario here. So either 5 minus 2x is greater than 10, or 5 minus 2x is, flip the inequality, less than negative 10. Solve them independently. This one, subtract 5 from both sides, so negative 2x is less than negative 15. Divide everything by negative 2, and x ends up being greater than 15 over 2. Or subtract 5 from both sides, so negative 2x is greater than 5. Divide both sides by 2, and x ends up being less than negative 5 halves. So this is my or. Next step is to graph it. I have my negative 5 halves. I have my 15 halves. So less than negative 5 halves or greater, excuse me, I think I said that wrong. X is either less than negative 5 halves or it's greater than 15 halves. That's exactly what I expect my or statements to look like. So negative infinity to negative 5 halves, in this case it's soft and soft, union 15 halves to infinity, also soft and soft, because it cannot be equal to it. That is what a typical or problem, examples 1 and 3 are what a typical or problem should look like. I'd like to do one more problem, and this covers the special case scenario that we talked about in class today. So number 4, and this will involve a negative number. What if I had the absolute value of x plus 7 is less than negative 8? Think about it conceptually. Absolute value of a number, even if you add 7 before doing the absolute value of it, this is automatically always going to be a positive number no matter what. And I want to know, when is this positive number going to be less than a negative number? I wrote that wrong. This isn't supposed to be a less than problem. Start over. Sorry, everybody. Absolute value x plus 7. I wrote the wrong thing. This is a less than. We're doing a greater than lesson. When is this going to be greater than? Greater than negative 8. Okay, sorry. Now I have to start all over with my deep thinking. Deep think, Elliot. On the left side, I have an absolute value. No matter what the value of x is, even after I add 7, even if I subtracted 100 or whatever, you apply this absolute value, the left side of this equation is going to be positive. On the other side of the equation, I have this negative. So this is kind of asking you, when is a positive number going to be greater than a negative number? When will a positive number be greater than a negative number? And that's always. No matter what number you plug in for x here, it will always be a greater than negative 8. So the true answer for this one, I'm going to write it on the side, is all real numbers. Every single number that we know of that's real, if you add 7 to it, take the absolute value of that number, it will be greater than negative 8. interval, I guess graph is the next typical way I talk about it. Just in a big, full, happy graph. So I just include 0, but then you've got this line that goes forever in both directions that shows all real numbers is what the solution to this is. Interval notation, negative infinity to infinity. This is how you'd go about this answering this problem. Now, that's common sense. And if you see this problem like this and you're like, oh, I get it. An absolute value will always be greater than a negative. You can just go straight to this answer, boom, and you're done. If you don't see it, the math will help you get to an all real numbers answer as well. If I go like this, x plus 7 is greater than negative 8, or x plus 7 is less than negative 8, start solving. Subtract 7 from both sides, so I get x is less than negative 15, or subtract 7 and x is greater. If I subtract, wait, I've made a mistake. Positive 8 here. Flip the inequality, change the value. So in this case, it's negative to positive. I gotta start over then. If I subtract 7 from both sides, I get positive 1. So I get x is less than positive 1. Or if I subtract 7 from both sides of this equation, I get negative 15. So I have x is less than 1, or x is greater than negative 15. Something doesn't sound right about that. Let's graph this on a number line. If I have negative 15, I have positive 1, less than positive 1, or greater than negative 15. And with or statements, we do not need that overlap. So it's always working for these values less than negative 15. It works in between 1 and negative 15, and it works greater than 1. When you have overlap in an or statement, that means all real numbers. So at this point, after looking at this answer and looking at this graph, you would then come up with this conclusion that the answer is indeed all real numbers. And then you graph this number line to demonstrate that it works everywhere, and you answer negative infinity to infinity. Okay, so that is absolute value inequalities of the greater than persuasion. As a friendly reminder, these greater thans, they are or statements, then they should look like this. And if you set up this or statement and it looks like this, the answer would be in all real numbers. That's your special case scenario, and it only happens when it's greater than or equal to a negative. So anyway, everybody, I hope you're having yourselves a fantastic Monday, and I'll see you soon. Bye-bye.